Good morning, David.
Morning, Pam. How are you?
Not too bad. How are you?
Very good. So Rob can't join us today, I don't think, and we'll see if Rose can make it, but it might just be the two of us. We'll see. So I did get the PT deck stuff working that you shared last time. So I was able to reproduce their result. And then on Wednesday, I chatted with Rob about how we might want to apply that to time series data. And it's not obvious what the clusters that we're looking for are in the economic setting. Like, it's just, what does it mean to do it? So I'm not doubting that the algorithm will work. I just don't even know what the question is I'm trying to ask, as it makes sense. But
yeah, makes sense.
But and did you have a look at the paper? It's fairly long and not very easy, but
I think I've looked at the paper before, but I watched instead the machine learning street talk interview with Carl Friston, and there was also another sort of interview with him that was pretty good. Yeah.
So what's your take on it all?
Yeah, I guess my immediate reaction was, of course, like, everything is pretty simple. Like, it makes sense. Like, there's nothing. And I think it's not falsifiable, as he also admits. But yeah, it's interesting. Hi, Rose.
Hi. We haven't got very far. We're just chatting. So
okay.
So Payam's seen the paper before, but he watched the video, the machine learning street talk interview with
Carl.
Friston. I can never pronounce his surname correctly yet. Did you have a look at the paper or the talk at all?
I had a look at the paper and I decided that I was not in the frame of mind to get into that. And so then I went back and just started watching some YouTubes, and I'm not very far into the street talk one. I did some of the more general ones where he was just discussing the ideas.
Just to let you know, Rob can't join us
today.
Yeah. So Rob can't join us today, sadly. But
okay.
Yeah. So so there's many pieces to it. One of the kind of side notes that I thought was really interesting was that he felt quite confident that we could generalize by ignoring time series of granular events. So he makes the distinction between perhaps, Pam, you have better words than this, but basically the large scale versus the fine, the coarse grain versus fine grain. Is that the right language? I'm not sure what the right language is. But his claim was, which is highly relevant to what I've been thinking about with Rob Neal, is that if you have a situation where you're trying to form a coarse grain inference, if you're trying to do a coarse grain inference and you have a lot of fine grain data, it's fine to ignore the sequence of the fine grain data. In other words, you can just sample from the fine grain data randomly, and that's good enough for high level inference, if I got that right. Does that make sense to either of you, that it's legitimate? If we have, let's say we have a whole bunch of time series for patients, let's say, okay, and we have classified those patients into some form of cluster. My understanding is that if you're trying to gain a high level insight about a particular patient, you don't have to draw on samples in a time series. You can just randomly draw from their historical data and form a high level opinion based on that.
So I didn't get far enough in the Friston stuff to see the connection, but the immediate reaction to that is that can't possibly work. But
okay.
But
right.
I might be missing something.
Okay, so why? Well, I may have missed it as well, but go ahead.
I guess I was going to say I have a slightly different take on that, in that I think this idea of embodiment is really important. And he's talking about it from a neuroscience perspective, but even outside of that, there is a piece of embodiment that happens where we take something that is an idea or a potential and we materialize it in some way. And so when we're talking about
We lost you, Rose.
clustering patients or can you hear me now? No.
Yes.
Okay. When we're talking about categorizing patients, I think of that as a form of materialization. So you're basically creating, how can I say this? You're creating some form of structure that didn't exist before. Are you guys with me or no?
I guess my issue is with the word creating. Like, are you discovering? Are you implying? Like, creating is maybe too strong because you're not creating any structure. The structure was always there, depending on given your algorithm.
So I think that's a really interesting point, and it comes down to his thought about we see things in terms of their potential for us. So we don't see things as they really are. We see things in terms of their potential for us and how we can manipulate them.
That's fair.
And so that idea of creation is really important because we've taken something and we've recast it in a different way because that's the way we can understand it and that's the way we can interact with it.
But again, I guess.
And so before we ever.
But his whole idea was about prediction, right? Like, so you form a model and you evaluate it based on this predictive value. If it's always predictively correct, I would say that is by definition the correct model.
So, okay, yes and no. And this is why it's important to talk about this, because he's also talking about a dynamic interaction that's happening, right? And so once you've created things in a certain way and you take actions on them expecting a particular output, the chances that you see what you want to see, and actually the chances that you get the effect that you want to, because you've gone now from passively observing something to actively doing things to reinforce your model of the world. And it's only when your model of the world is really broken and it's just like, oh, my actions are not doing what I want them to do anymore, that you realize.
That's a great point. I mean, it might actually be a viable strategy, right? Like if you are inside that Markov blanket, you can either get a perfectly accurate model of the world, or you can make a world where your predictions are always correct. So I guess both of them are happening at the same time. And that's part of the strategy of survival. You make the world so that you can predict it, so then you can survive better in it.
I mean, that's his point, I think. And that's why the embodiment piece of it is so important, because we think that we're seeing things as they really are, but we're not. We are altering ourselves and altering our environment to basically align in some way. And so when you're talking about patience, I think this becomes really important with patience, and sort of to get back to your comment, I am of like, that can't possibly work. It can work insofar as we materialize the category in some way. So if you stop looking at the fine-grained stuff and you now define the patient in terms of they have this disease, this is who they are, this is the patient, then you can just sample from the other stuff because it no longer matters, right? The other stuff, you've materialized a category that has now become the new object within the model. And so your predictions are going to be about that new object rather than about the patient as they really are.
I think that makes sense. And I guess, again, like as so far as that would help the patients and you to do a better job, maybe that's okay to do that. But I think you have also mentioned lots of ways that can go wrong, right?
So I think it's that balance, right, of understanding when you have something that's useful and when basically you reaffirm to yourself that something is useful because you're looking at measures and.
Yeah, I think he calls that self-evidencing.
Yes. And I mean, I think he talks about that, right? Like in a way, what you're trying to do is reconfirm for yourself that your model is correct constantly, right? Whereas I think if you're a good scientist or you're a critical thinker, it's back to the explore exploit, right? Am I really understanding what's going on here? Or am I just confirming to myself what I thought going into it is already true?
But in a sense, I guess the maximum free energy principle, I think it's maximally flexible, right? So you basically only try to fit the model at a very, very minimum way so that you preserve maximum flexibility for new information. So in that sense, I guess there is no, like, that's one of the points he makes, right? It solves the problem of exploration, exploitation, because these two are balanced perfectly. And I think one of the street talk people brings up the point, like, do we add a weight of which one do we care more? And then he talks about extensions where you could do that. But in the main part of the theory, there is no explore exploit. Given the information you have, there is a perfect way to balance like flexibility with the way you fit your model. So
that piece of it, though, given the information you have, that's kind of the crux of the issue as far as I'm concerned, right? How do you know when you need to recast what it is you're looking for? How do you know if you need to go out and do a search for additional dimensions, for want of a better word?
I think his whole formalism is Bayesian, right? So I don't think it allows for new constructs. Like you can update your belief about a state, but if you want to add a new state variable, I don't think he addresses it. Maybe I didn't get far enough. I don't know, David, did you see any way to change the model structure completely? It seems to be just you have a model that maybe has a bunch of parameters and you keep updating your belief about the state.
I think this is where it links in with some of the other stuff we've talked about, though, because if you can disprove your model in certain situations, and that's when we get into to David's idea of jumping a level up and recognizing that, oh, we need a new model here. We need a higher order to say like, oh, this model is appropriate in this situation, but we actually want a whole new set of actions and objects in this situation. Or we want to at least explore, is there a new set of actions and objects?
So very interesting, and I'm not saying no to anything you've said. I'm just trying to draw on what I picked up from the material. He talks about there being sparsity. So he talks about there being sparse correlations. So essentially, he's saying that, and this is similar to what Benjio was saying with his G-flow nets, was that we can sample, oh gosh, sorry, it's a very difficult translation. Carry on, sorry, I'm just trying to, I'll bring up the paper perhaps. Yeah, so basically what he's saying is that we start off with soup, right? So his initial, the Levitin, or once again, the Levitin or whatever it is, model, as I understood it, was basically everything is connected to everything else by a spring, right? So it's a fully connected network where everything affects everything, right? And that's kind of the lowest state that you can have, which is what he calls soup, which I think is basically the same word that I came up with. All right, and then in order for things to distinguish themselves from the soup, the only mechanic he allows in his model is the Markov blanket. So if you can surround yourself with a Markov blanket, then that the mere existence of that Markov blanket around you defines your ability to even be a thing and not just some more of the soup. And so in order to define a Markov blanket, you have to have not marginal, what's the opposite of marginal? Gosh. Conditional. You need to have conditional independence between things. And if you have conditional independence, then you can start to form a Markov blanket. And if you can build a Markov blanket, then in his words, you can legitimately call yourself a thing or an agent or something. So that's kind of the first tier of it that I understood. And I generally agree with that idea. So we start off with some data and we just assume that it's a soup, right? Everything's connected to everything, it's just a mess. We look at the data, we play with the data, and we find invariances using KL divergence. So we find these sparse linkages. And then from those sparse linkages, we can essentially define a Markov blanket. And then once we have a Markov blanket, we can say, ah, that's a thing. Right, that's something that is a thing because it has a Markov blanket, it fulfills these criteria, and therefore it's distinct from the soup in some meaningful way, and we can assign it properties that are unique to it and not just the amorphous soup.
One thing, yeah, I think that makes perfect sense. And one thing that came up in the street talk, and I don't know if he mentions it in the paper, was somebody asked, like, is that Markov blanket, I think in his model, the Markov blanket is set, like you are that entity inside the blanket and there's the outside, there's inside. But he said there are people working on a dynamic Markov blanket where I think that's what we need maybe, because that will give you more affordances inside because you get to exert control over more things that you used to have control with and also access more stuff outside. And I think he mentioned somebody famous, some Russian mathematician who's like does ergodicity. Yeah, I think so. Yeah, ergodicity and that sort of thing. And there is some concept of flowing sets where you have sets of things and then you can flow more elements or less in and out. I think that might be the key to maybe like gradually increase our action space or model space.
So that, yes, so wandering sets he talks about extensively in both of the machine learning street talk videos. Yes. And so the idea is, as I understand it, and I will share my screen. I'll just make this a little bit less ludicrously big so you can actually see it. One sec, and then I want to go to this picture. Sorry. Scrolling through ridiculously long. It's not there. Okay, let me share my screen. Anyway, so I'm trying to get back to your point, Rose. So I'll continue to kind of grind away at that. Okay, so, right. So what he is saying is a little bit more rich than that. So he's saying that a precondition of being a thing is that your internal states are conditionally independent on external states and vice versa, right? So there has to be some level of isolation or insulation between one participant in the system and another in order for them to be distinguished as different things. And so he's saying that there is a flow from the external world, external states into the sensory states. And then this essentially has correlation with active states, which then can change internal states. As internal states change, they will change your active states, and then those will affect the real world. So this is your action space, this is your perception space, this is the external reality, this is your internal, Kant's apperception and inner sense. So it's kind of backwards because he's not saying that things have this. He's saying that in order to be a thing, you have to have this, right? This is the definition of thingness. And if everything's like fully connected and you're just in the soup and everything's connected to everything, you can't claim any kind of independence. So that's the first kind of deep point I got out of it. And then there's another picture down here, which is useful. So remember I was rattling on about fixed points.
Can we go back for just?
Yeah.
Can we go back for just a second before we get into the more?
No, that's fine.
Can we go back up to the diagram?
Is this not the diagram?
There we go. Yeah, it is. Sorry, I think I was a couple seconds behind you.
Okay.
So what's really interesting about this is the idea that our internal state is self-reinforcing.
Yes.
And actions in order to make that happen. Right? So that's your thingness.
Yes.
Is constantly either changing your internal state or changing the external environment to match your internal state.
Well, you're not
That's
trying
what
to
makes
match it,
you,
because that would then, you would just dissolve back into the soup, right? You would be quote unquote dead. Right. So you have to maintain the conditional independence between your outside and your inside, right? But no, I'm not suggesting there isn't a pattern by which, so all he's saying is in order to change the outside world, you have to take an action. And when you take that action, it has two effects. It changes your internal state and it changes the external world. Okay.
Another thing that makes it interesting is, like, imagine you are in some vegetative state. You have no active states, no sensory states. You can still modify your internal state, I would say.
Absolutely, sure. Yeah, yeah. If you're an alien floating in space, nowhere near anything, there is no external anything that is meaningfully interacting with you. Yeah, you can change your internal state. It's arguable whether that, you are a thing because there's nothing else, right? So
no, but there could be something else. You just don't have access. Let's say the connection from the outside, the Markov blanket to you gets severed.
Right.
Not that it doesn't exist, but
that's a great point, and it's also the piece of your sensory perceptions only allow you to see what you're allowing it to see, what your embodiment allows you to see. So there's severing, but there's also taking in and adding out, right? There's all this stuff going on out there, but I won't see it. I'm not going to acknowledge that because it doesn't fit into my model.
Yeah, so the way that
doesn't fit into my internal state.
That's right. So the way the geometric deep learning people talk about that is they say that the nodes of the graph that you're doing the learning on are essentially the geometry of your sensor network, right? So if you have a camera with a grid of cells and you show it very, very high frequency information where there's so much information between each kind of receiving pixel that that information is lost, that's an inherent limitation of your sensor that has nothing to do with anything. And so the sensor can only sense what it has, essentially the data only lands on the nodes, if you will, right? It doesn't land anywhere else. So if you don't have a node to receive a certain kind of data in your sensor network, you will not get that information. We're talking about severing that, yes. So if we edit the graph of your sensor network, that will preclude a whole bunch of information arriving and actually having any effect on your internal state. So the design of your perception apparatus is critical in order for it to have sensitivity to the things that you care about in the outside world.
So can we talk for a second? Does that relates to time series and fine grain and coarse grain? So like in a way, often what we do is we sort of discretize some time series or something into a yes or no, right? Like you put it into a category or not. Mm-hmm. And so if your sensor is just saying this is or this isn't, probably sampling, is that true? Probably sampling at the fine grain, you don't even need time series. You're just going to, that probably is true. If you just sample across everything, you're still going to arrive at the same, you would still arrive at the same categories.
It's an interesting question. I don't have the answer. So I just wanted to talk very briefly about this idea of autonomous states, this one here. So that's why I was skipping on to the next picture here. So his claim is that this is autonomous flow. So if you have a particle and it's in it's near a fixed point, then it will do exactly what we're talking about when we're talking about fixed points, is that it will be sucked in, right? If you're near a gravitational object, you'll get sucked into it, right? So that is essentially your autonomous flow. And the idea of wandering sets is that the fixed point itself is drifting, right? So this spiral, like, you know, you're on some spiral to go to this fixed point, but the fixed point itself is moving. So you're essentially being doubly moved off this. I'm not sure if that's very clear. But the idea of wandering sets is that when you place an object in the environment, there are a bunch of fixed points in the environment that are essentially creating gradients, which the principle of least energy, or the he talks about path integrals, right? You want to find the path with the least energy. That path of least energy is deeply affected by these fixed points. And okay, but the problem is the fixed points might be moving. They're not fixed, right? They're wandering. So you still have these kind of attractors moving around the environment, but they're actually moving. And so the optimization problem never ends, right? If it was a static environment, then you could possibly find a solution and maintain a state for a long period of time. But if the underlying attractors that are driving your behavior, this autonomous behavior, are themselves drifting, then you know, you're essentially in a situation where you're not in control, right? You're being driven by these autonomous flows, and you're trying.
But isn't that just life? I mean, that's adaptation, right? That's the whole purpose of this machinery. If there was a fixed point, it would be pretty boring. You just get optimized, and then you will never change your belief state, and you will be fine for the eternity, right? I mean, the whole point of this is to keep that entropy high enough or low enough that you can adapt to it as fast as possible when things change.
You've got it. Yeah, your understanding is perfect. Yeah, that's the same. Well, I'm not saying it's perfect because I don't know, but that matches my understanding. Yes. Mm-hmm. Yeah. So yeah. So he comes up with this whole very elaborate kind of language around all this, where he's actually defining, so there's this idea of self-referencing, which I think you were getting at, Rose. So let's touch on that one very briefly. See if we can. Not sure if that one's this one. Sorry. I only understood bits of this. I certainly didn't understand it all. I'll go back.
A lot of math in there.
Holy crap, yeah. Some of it I understood, but most of it I didn't. So this is his version of, do you know what saccades are? Are you familiar with saccades? So when you look at something, you don't look at something. Your eye actually pops around and kind of jumps all over the place, and you know, and these eye tracking systems that try and work out where you're looking don't work. Not because they can't see where you're looking. It's just that there's a whole subsystem in your eyesight which is actually jumping around. That's when he tries to explain that. No, I think I've gone too far. Okay, so there was another picture where he talks about self-evidencing. I'll just search for the word.
Do you mean by that it's like internal attentional?
No, he's saying that there's an action perception loop. Are you familiar with action perception loops? So you move your hand, you see that your hand is moved, and then you update the position of your hand based on what you saw, and so you kind of go in that loop. Yeah.
But by saying that the eye tracking doesn't work, it's also because the eye tracking movements are too coarse to understand the internal.
No, there's an interventional system between what it is that you find salient and what is driving your eyeballs. Like there's another little person between you and that higher level person, which is trying to flip these your eyes around to try and make sense of the term, the world. And he calls that another term that we're familiar with, which is artificial curiosity. I think that's what Schmidhuber called it. So how are we? So basically, what he's trying to say is that you could use the free energy principle in an unsupervised learning framework and actually make progress. Is my understanding. Is that your understanding, Payam?
Yeah, that sounds about right. I think he also mentions like the whole model predictive control, right? I mean, what he's proposing is very related, right? Like a Kalman filter or something. So you have some model, you predict what will happen, then you take some action and you adjust your model and you keep going, right? And I guess from what I understand, basically that's what he's trying to do, but with a more basis on physics and entropy and all that stuff, just a different language.
Yeah. Yeah, I mean, I felt he missed a couple of really important pieces of the puzzle. Like he doesn't talk about prospect theory at all. He doesn't recognize. So he talks about, remember how we were talking about with that manifold picture I have where moving around the manifold this way, you're moving, but you're certainly not getting out of it. So he actually calls that solenoidal flow. So if you're flowing around the surface, but you're not actually gaining or losing altitude, if you're not getting closer or further away from the closest fixed point that you're currently trapped by, he calls that toroidal. And then he has another name for trajectories that will actually either take you closer to the fixed point or further away. So he does make that distinction. He's trying to come up with a way of building a reinforcement agent that can move through an arbitrary world with arbitrary sensors and do the best that it can, as I understand it.
I think he talks about model-free and model-based reinforcement learning. At some point, he brings it up. I guess his theory is pretty high level, right? Like, I mean, I don't know if it gets into the, maybe it does later, like into the machinery of how you would actually like implement a system that do that, right?
He does. No, in the paper, he actually
does. Okay.
That. Yeah.
Okay. Good.
Yeah. He actually he's making a claim, and that's fine. I think that's cool that he's making a claim. But he's making a claim that you can actually do that you can actually create an agent that will be sentient to the limit of its, ability to interact with the world in some way. It will minimize its free energy. It will try and find these path integrals that actually have the least energy to get to the. He makes this huge distinction between the density over states versus the density over paths. Are you familiar with the distinction?
Nope.
So what's your understanding of Feynman's theory that he got the Nobel Prize for? I've forgotten the name of it.
QED
electrodynamics. Yeah, so he uses.
I mean, I understand path integrals pretty well. I mean, that's what you mean by the density of the path?
Yes, so he's basically saying that the free energy principle, when applied, will yield the minimum path, right? The least energy path.
Yeah.
In category theory, this is called the universal construction, whereby you essentially define some filter that defines the possible space that you're looking in, and then you have some ability to compare two samples and to say this one's better than this one, and then basically you take the limit of that and you end up with this optimal solution. So he's saying the same thing applies to agents that use the free energy principle as their underlying reward function. Not sure.
Yeah, I mean, for the path integral, I guess, at least in the physics, I don't know, it might be different here. Like once you set up the path integral, you basically integrate over all the possible ways you can go from one point to the other. And just because of it's a complex sort of integration. So all the phases of the path that is not the fastest route, like a straight line, will cancel each other out. And then you end up with the fastest route. So it's just a trick of, you don't have to assert that you will go through the fastest route. You just set it up as if you're going through all of them. And then when you do the integration, it turns out that all the other ones cancel out and you get the fastest route.
Okay, yes. So he alludes to this extensively throughout his work, and that's his claim as to how you can achieve some form of optimality without having to construct a model first. Yeah, so my understanding is that you can impute the existence of things by searching for invariance in the data. That invariance will lead you to construct a Markov blanket. And if that Markov blanket has certain properties, we can use that Markov blanket to define a thing as a thing. So let's say we ran the DEC algorithm, the unsupervised classifier, on a system. One thing we could do is we could actually try and apply that rule to the things that it finds and see if they actually qualify as things, right? So it says, I've clustered these things together because I found some form of invariance. We might be able to formulate a test where we try and construct a Markov blanket around that. And if we can, then we can say that's a valid category and we can make the claim that we've actually discovered something. But if we can't make that claim, then perhaps we can't. Yeah, so I'm trying to map this back to the categorization stuff we were talking about last time, like trying to come up with clusters in the data. And the other thing is that this gets to Rob's point around the distinction between cross-sectional data and time series data. So you can think of path integrals as occurring along a time series, right? So you're integrating along the trajectory of a patient, right? So they were born here and then they broke their leg and they lived in a polluted city and then they took up smoking. And so there is a path that you're integrating across to try and find, where they're at, okay? As opposed to cross-cutting concerns where you just sample across all people who have lung cancer and look at, try and determine some invariance about their past history. I think that's the distinction between path integrals and density states. But the path integral stuff kind of goes against this idea of fine grain, coarse grain, right? Because if you're at the coarse grain, can you perform path integrals? I guess you can. I don't know. Sorry, I really don't know. So if we have a ton of data and we're trying to come up with a single Boolean, which is approve this medication or not, do we do cross-sectional or do we do
I think you're making an assumption, right? Because if you want to do the path integral properly, you need like infinite trajectories of a single patient and then see what happened, right? Which is never going to happen. So I think we take the shortcut that we take different patients and each of those paths, we take that as a path. And then we assume they're all the same patient, just that went through different things. And then you try to extract some kind of results from that. So I guess that's probably the crux of the problem. You can't do path integrals in real life. You can do it in physics, but you can't because you only get one trajectory per person, right? Like how can you do path integrals?
Isn't that when the clustering comes in to get to the cluster in the first place? So you have different types of people and you identify.
Yeah, exactly. So to approximate this path integral, you clump people together and say it's actually the same person that's gone to a different path. But if they're similar enough, then maybe you can count each of those trajectories as part of the same sort of path integral, right?
Right, but looking at the time series across the cross-sectional data doesn't make any sense, right? Which is his claim that you don't need to worry about the sequentiality of the data in a cross-sectional sense. If you're trying to do coarse grain inference.
Well, I mean, that's how reinforcement learning, I mean, that assumption is made in reinforcement learning too, right? Like you do a bunch of simulation to get these trajectories, but then you sample from them at random. You don't look at the order. And yeah, so they want to, in a sense, be insensitive to the order that the information came because you just take each piece of information as a separate data point. But I don't know if that's ideal or if it's just necessary from practical perspective, because otherwise you can't do anything. So I don't know, is that something we want or is that something we just can't do without?
So in my situation, I have agents that move through an environment, right? So they start off in their apartment and they go shopping and then they come back and so on. So I'm doing, all of my stuff is path-based. Like I don't do any cross-sectional. I essentially, what I do is I look for events in the paths. So if I see you on my walk, then that's an event. And I record that event. But that event emerged from the intersection of two path integrations, right? Where I'm essentially marching down the paths, the timelines, the lives of these various different agents and seeing where their paths cross. And he doesn't seem to address that in this work. Like he doesn't talk about path integrals that intersect or anything. He sees it all as one. I don't know. There's a decoherence there for me. So in the physics sense, you have a mathematical model, which is very accurate. And then you integrate across using mathematical tricks. You integrate across all possible paths to find the path integral. Is that right?
Yeah, I mean, in quantum mechanics, it's even like one step further. You're not even saying that there is a unique path that you're trying to find, the best path. Like in quantum mechanics, the particle is actually going through all the possible paths. And by integrating it, you know what you would observe. So because there's this particle wave duality, right? So a wave goes through all the paths at the same time. So all of it is happening. So by integrating, you will get the most likely or the actual observation that if you do the experiments, you will see that path. So that's even a higher, I don't know if that's applicable to our sort of scale of things, because obviously for a patient, we don't say that the patient is going through all the possible ways he could have gone for it at the same time. You could, but most people don't say that. So we are trying to find the actual likely path. So there's that distinction. I don't know if it makes any difference from a practical perspective, but.
So what do we make of this? Is this useful, or is this just really interesting, deep theoretical work that has no practical relevance to what we're doing? Has somebody actually successfully used the free energy principle to do something?
I think he talks about like mapping a lot of the stuff people are doing already to his principle. Right. I don't know if it actually adds something to like, this is a better way of doing it. It's just a way to understand everything in one framework that's general. At least that's what my understanding was.
Wasn't he doing some stuff with EEGs?
Yeah, no, he is the leader of
to try and look across functional areas within the brain and identify like linkages between different functional areas, as opposed to thinking this all happens over here. It's a dependency between these two things.
But can't you do all of that without like talking about the free energy principle? Like, I don't know if what this brings, because all of that is like all the math you do to correlate things, to relate things, like statistical stuff is independent of your big picture understanding of what is a principle. Because I mean, they mention it in the street talk that it's an unfalsifiable theory. So that already tells you something, right? Not that it's wrong, it's just it's a framework, a way of looking at things. But if you can't experimentally verify if it's true, then it's not really useful, I think, in practical application.
I see. So it's just a mental frame then.
Because he mentioned other competing theories too, which is kind of, it's almost funny. Like they're all maximizing or minimizing something. There is like a maximum redundancy principle. There is the minimum, whatever, falsifiable print. Like there's all these, basically you take some quantity you like he takes the free energy, and you basically say brain is trying to maximize or minimize it, and you get a whole theory out of it. So I think whatever you can imagine that you want to maximize or minimize, and you can attribute that to what the brain does, you get a new theory. And I guess we just maybe don't know what the brain is actually doing. Maybe it's not actually maximizing or minimizing anything. I don't know.
Maybe it doesn't matter though, in terms of what we're trying to do. Like, we don't actually have to replicate what the brain is doing.
Yeah, I mean, he's a neuroscientist, right? He's just trying to understand the brain. I don't think his main goal is to develop algorithms, right? So his goal is to understand the brain and have a theory of intelligence and psychology, right? Like he said, we started out by trying to mathematize psychology. That was his goal in college, right? So,
right. Okay, interesting.
So I think that the thing for us is if we have an entire set of data of whatever type, financial, healthcare records, whatever it is, can we use this to try and find some embodiments or materializations of things that we wouldn't otherwise have discovered when we've taken a more theoretical approach to it? Here are the categories as I know it today. Can we find new ways of grouping things that could be useful?
That's one way we could do it, yeah. I'm not saying that's wrong, but another way we could do it is we could use the free energy principle or ideas from his framework to validate or score other algorithms, right? So we might have an algorithm that we know can find good clusters, right? We have k-means, we have DEC, we have these other things. We don't know what we don't know, but if this thing is saying this is salient to me, then we might want to be able to apply a test to that thing that the agent is telling us is salient to see whether it's worthy of thingness or not. I found that to be useful.
Yeah, as far as I can tell, like the machine learning community or math or optimization, they're already doing that. It's basically his maximum whatever free energy principle is solving the bias variance problem, which is like it's very well understood. You're trying to minimally assume things and then maximally be open to new things. That's all it does. And every machine learning model, every statistic model is already doing that. So to take that, and I think the rest of it is just a nice story of physics and neuroscience and maybe backed up by experiments. But the basics of it is I think everybody accepts it and already is incorporated in everything, right?
Okay.
But I don't know if you can like take the bias variance issues. Basically, he's doing Occam's razor, right? Like don't add anything extra to your model unless you have to, so that when new information comes, you can change your mind faster. Is that useful to come up with new categories? I think it's probably useful, but that's the new thing you have to add on to it, right? How do we expand our categories to maybe still meet these criteria?
The piece of hypothesizing around the Markov blanket too, right? So you've identified something that you think is a Markov blanket, then validating, is that true? Right? There's some element there of, okay, you have the variance, you've identified some cluster, then you have to come up with some hypothesis for what the Markov blanket is, right?
Right.
And that's the useful piece. Because if you see that the Markov blanket that you've defined, which basically gives you your set of actions, if that's incorrect, then you need to look for something else. You need to switch the model.
I mean, they briefly go over like a set of things that he didn't know how to address with the Markov blanket, like a hurricane or an open flame, right? So maybe that's the sort of thing we want, because you can't draw a clear box around it because it's influenced by many different scales and many different time scales. And he said they're working on it, but I don't know, but it might have already continued his work. But I think that's important, right? That distinction is not always concrete.
See? So I have a slightly different kind of take on this that I think might be useful, if I can just share my screen for a moment here. So if we have some Markov blanket here, right? So we have some sort of kind of points, and then we have some Markov blanket where the states are coming in. Sorry, it's very hard to draw on the mouse, but so we have some Markov blanket. So what he's saying, as I understand it, is is that if you have a Markov blanket that is very deep, it becomes very brittle, right? So to me, when we're trying to create our model of the world, when we're trying to induce our understanding of the world, if we create Markov blankets that are very deep, we're essentially overfitting, right? We're applying many, many layers of intervention one after another, which are all based on preconditions and expectations further up and further down the blanket. And so to me, one of the things the free energy principle is trying to say is that if you should try and have minimally deep Markov blankets, if you will, right? You want the Markov, if it's zero, then you're just in the soup, right? If there's no Markov blanket at all, then your thing is vaporizes and you're just, part of the soup. But if you go too far, then you become so distant from your external environment that your ability to react to new stimulus and to complex drift in the external world might be compromised. And so he's saying that you need to kind of, it's, no Markov blanket means you're not distinct. Too much Markov blanket means that you're so isolated and you're so distant from the outside world that the chances of a perception or a percept in the outside world having an effect on your internal state is very, very unlikely, or at least very unlikely to emerge.
I don't think I'm getting that piece of it. Can you say that again?
Sure.
So the Markov blanket is your internal state, right? So you're already
So when I interact with the world, I have my internal state over here, right?
Mm-hmm.
All right, and I'm going to go through this Markov blanket to change something out here in the external world, or vice versa, right? So there are two Markov blankets that are going like this.
But you have a model of that in your internal state too, right? But then you have those same components, right? This is your working model. Your Markov blanket is your working model of what's happening. This is internalized.
So if I'm trying to construct a law for a country or a medical system, and I create a really, really deep and complicated Markov blanket of steps that it's necessary for a change in your internal state, I don't feel well, to have an effect in your external state, you go into hospital. If there are too many steps in your Markov blanket, if there's so much bureaucracy and so many tests and so many kind of limitations that for you to fight through to get to the end, you will essentially become very decoherent from your internal state will become very, very incoherent with the outside world, right? Because it's so much energy, so many steps, so many actions, so many things that you have to do in order for your internal state to have an effect on the external world and for your external world to have a thing on your internal state. You need to.
The piece I'm not getting from what you're saying is I think the internal state and the external state are the same. You have to have copies in both, right? It needs to exist in the external state, and you need to have a representation of it on your internal. I mean, you're saying the external state is you go to hospital, but the external state has all of these nodes too. It has more than that. It's just that this is your internal representation of it. No?
It's not the internal representation, it's the actions necessary to get there, right? In order for me to get from here to here, I have to go to this node and either this one or this one. And if I get to this one, then I have to go to this one, and then I have to go to this one, and then I can get to this one, right? So your action space, if I provide an affordance to you that does this, right, that just takes you straight to hospital, and there's no Markov blanket, then it doesn't mean anything, right? Because you're not a thing anymore. It's just one big amorphous mass. And, I go to the hospital when I feel like it, and they look after me if they feel like it. And there's no action space, right? I don't fill in a form. I don't do anything. It just kind of happens organically. And if there's too many steps, then essentially the medical system is useless because nobody can fight their way through the Markov blanket to actually have their internal state be affected by the external world and vice versa. All I'm saying is that the way in which we construct our action space, our Markov blanket, is pivotal to the success or failure of the model in both ways, right? not enough is not good and too much is not good. So we need to kind of have somewhere in between. Not sure if that makes much sense. So if we create heavy bureaucracy, if we create many, many steps that you need to go through, that acts as an impediment to information flow, right? And no, you're not sick enough, or no, you don't have the right symptoms, or no, you're too young, or you're too old, or you're too black, you're too white, or you're too something. It creates problems when it's too deep. So by simplifying the system, it might make it more effective. I don't know. That's one insight, I guess. But perhaps I didn't explain it very well.
You see, I guess even with the Markov blankets, I think that there are layers of abstraction even within that, right?
Yes.
And so depending on who you are and the action space that you're in, you might be thinking of it in terms of a set of actions to get you to hospital. Whereas if you are a physician or a hospital administrator or something, it's an entirely different, or
yeah, that's the backflow. Yeah, that's a different Markov blanket going the other way.
But it's maybe it's the same Markov blanket, but it's a different level of granularity. The things that are important to you and the actions that you have are different. But ideally, causally, it's the same. You might not need to know about all of those actions.
Right.
Right? But if we have a consistent Markov blanket across layers of abstraction, it shouldn't matter.
So do we construct a Markov? So in certain situations, the Markov blanket is latent, and we want it to emerge from the data. And that would be, I would argue, something akin to causal discovery, right? So you're trying, you've got some data, you don't know what it means, and you're trying to infer that. That's one use case. There's another use case where we construct Markov blankets as a matter of policy, right? We just do it by hand, right? We create healthcare systems and laws and countries and other things. And that's not derived from the data, right? That's kind of manufactured by some process. And all I'm suggesting is that if we're engaged in trying to build optimal models, one of the things that we should consider as a metric is the depth, the number of actions necessary to get to a specific outcome, and is that appropriate in some circumstances? I guess that's what I'm trying to get to. So if we're trying to design a healthcare system that's fair, then one of the things that we should think about is the complexity of this, right? So Payam, you're making the claim that this isn't actually useful in terms of reinforcement learning as a reward function, because we can't really, we're already doing it, right? We're already trying to maximize our ability to cope with surprise in the model.
That was my impression. I mean, obviously I haven't dug deep into all the latest things that came out of this, but I mean, I don't see, I guess, anywhere you can change something in any of the machine learning models in a positive way. I mean, you can understand all of them in light of this theory, maybe. And so that it kind of like category theory for me, you can maybe understand things from it, but doesn't really help me do anything that I couldn't do before. I could be wrong. So yeah, but it would be great to find out if I am wrong, because
no, that's fine.
As far as I know, like the reinforcement learning community has no understanding or knowledge of this. So if there is something new here that can be applied in a practical way, I think that would be super useful.
Yeah, I don't understand the math. I don't understand the math. I'm not claiming that I do. And the problem there is because I don't understand the math, I don't know whether he's addressing that directly. And we can actually use this to build a reward function for reinforcement learning agent. But in principle, I think we could. So we could define a reward function that says, look for things that have a Markov blanket, right? And so we could have a unsupervised clustering algorithm run around that is parameterized in how it looks for clusters. And we could refine that reward function from just looking for clusters that have Markov blankets, right? Or have other certain characteristics. And if we move through a search space, like if we run paths through some model, how does that get us to?
I mean, just the whole like concept of Markov blanket is like a nice conceptual theory, but in practice, like how can you possibly know where the Markov blanket of something is unless you just draw it in the paper and go with it? Like I feel like that's already pretty hard to define in any like reasonably complex system, right? You can draw 5 circles on the screen and talk about it, but once you have 1 trillion circles, then I think it gets really tricky. Also, you don't even know which circle is which, right? I mean, he talks about the brain. I guess in reinforcement learning, each agent is kind of the Markov blanket, right? So that's what you're trying to control, and the environment is everything in the external world, and your model is your neural network or whatever that's trying to control the agent. So that's just a given. But to do anything beyond that, like I don't know what you can do.
Good question. Okay.
So if we can identify clusters, and then after we've identified the clusters, we do causal discovery within it to try and identify candidate
things, he calls them.
graphs, let's just say, right? So we have some that which basically give us a Markov blanket. So then we have a theory, right? Now we've taken this cluster that we don't know what it is. Is it useful or not? I don't know. But now we actually have hypothesis is already a strong word, but we have some sense of here's what might be happening causally within this cluster. And so we have some sense of, is there some new intervention that we can take with this cluster that is not an option with this other cluster because of the difference between the
Conditional independence. Yes.
But
right?
I mean, but in clustering, like there is no such a thing as do cluster and then something. Like do cluster based on what? And that's the whole point of the problem. Like once you decide what that thing is, then it will work. But you can go based on distance, you can go based on infinite number of things, and you will get infinite number of results.
So, but I guess the point is, are any of them useful? Right? So if you can, I mean, I think this is what they did with some of the cancer research stuff, is that they did the clustering, they identified, oh, there's something here, and then it took domain knowledge to try and understand, is this different? So if we have different cuts of patients that are like somewhere at the cell level or whatever, but then we can add additional layers of data into that we try and build Markov blanket. Oh, these are different because, and then does that give us a new set of interventions? Right, we never know if the cluster is useless to us unless we can do something with it. Right, we have to be able to take some intervention based upon the cluster, and that's what
essentially requires there to be a Markov blanket, right? Because if there was no such intervention, you wouldn't have a layer.
That's what the Markov blanket,
right? Yeah.
So it's combining those two things. It's combining the clustering with then identifying a Markov blanket, and then taking the next step to do something, take some intervention based on the knowledge that the Markov blanket has given us.
Can you explain again what is the relation between the Markov blanket and a cluster? I don't get it. Like the cluster is a bunch of points, your different patients that have some similar thing.
But are invariant in some way. Yes.
There is no action, there is no action, there is no state, there is no, I don't see the link to Markov blanket.
No, so then you have to take those, the clusters have been identified, and then you need to just go out and try to do some form of causal discovery to try and understand what can this cluster possibly mean. Is there some Markov causal chain here that can lead us to take some different intervention? Does that make sense to you or no?
I would have said it slightly different.
Okay.
I would have said that if we can infer there is a Markov blanket, then that very Markov blanket itself defines the action space, right? You could go here and then here and then here, or you could go here and then here and then here. Okay, so if we observe state changes, if we can observe the system is in this state, and then it moves to this state, if we can identify that a state transition has occurred, we can formulate a hypothesis as to why that state transition occurred, and we could essentially try and work out, using a hypothesis generation system, identify potential interventions that would lead to that state transition. And if we could identify those, then we could essentially infer an action space of some kind. Right. So if we have a patient being sick and we have a patient being well, and something happened between those two, can we somehow discover or infer an action or a Markov blanket, not the, but a, or a candidate Markov blanket that would allow that state transition to occur? It may be incomplete, but at least it's something. And now we're limited, our interventions are limited to the Markov blanket that we know. But if we could extend the Markov blanket or create new actions available to us that extend the Markov blanket, then the number of interventions available to us increases, maybe. But it's this multi-stage process where you look for invariants. Once you find invariants, you then look for state transitions. And if you can find state transitions, then you try and find actions. And then if you can find actions, then you can construct a Markov blanket. And then you can do causal kind of interventional studies.
Yeah, but I feel like in order to make it work, you need a closed loop iterative system. You can't just go in sequence and then go in sequence again and then go in sequence again, because so in the one extreme, if you do classification, right? Let's say you know what clusters you want, right? You label them, then you go, basically classification is an extreme form of clustering, right? Where you specify these are the clusters I want, give it to me. And then on the other extreme is you have no clue how many clusters, what's important, what's the distance. Then I feel like that's completely useless. I mean, you can go click on your Python and do k-means clustering all day, but it means nothing. I think it's completely useless. So somewhere in the middle, we need to find a way to do some kind of a light guidance, but verified by your testing at some point down the stream, and repeat that until hopefully you converge to something that has causal value. And I think some of these papers, the deck paper and all that, they try to do that. But as far as I know, like I haven't seen any silver bullet that tells you this is the way you do this. Maybe there are no silver bullets. I mean, I'm not saying there should be, but maybe it's just complicated. You use your domain knowledge, look at the clusters, does it make sense or not? And then you keep adjusting your thoughts. Like, but I can't think of like an algorithm that you would just run on any instance of this problem and that would give you the results.
So I guess what I'm thinking is that in the same way you can use, some people use domain knowledge, right? The causal discovery algorithms that are out there are trying to replicate that in some way. And maybe some of it is meaningless in the same way that clusters might be meaningless, right? Like you can define classifications because you're saying this is a thing, or you can just cluster and say, okay, I don't know if this is a thing or not, but from a data perspective, this looks like it might be a thing. There's enough difference here. But then to come along afterwards, the same way a domain expert might say, well, I think it's this, causes this, and this is why they're different. Can we do some causal discovery to say, oh, well, this is what the causal chain looks like here, or this is a potential, given this set of data, here is a potential DAG. given this set of data, here's a potential DAG. Is there anything we can see there that we can test and say, oh, this actually gives us a different set of actions that we can perform in this case?
But I mean, that's the problem of causal discovery that you're basically trying to solve, right? Yes, we can forget about Markov blanket, clustering, everything, throw away everything. We want to solve causal discovery. So that's like a separate problem, right?
Well, I think what this gives is that a lot of the time the causal discovery, there's a materialization that has already happened in terms of what we're looking for, right? We've already defined the elements of the causal chain.
We have a model, is what you're saying.
We have the model. So what we're trying to do is say, is there a different model? Is there a different way? Can we identify other things that actually are things that come with their own set of actions that could be useful to us? We're looking at the world this way, and what we're trying to see is there something else there that's out there that we just don't have the means to identify because we're not looking.
But that even goes beyond causal discovery, right? Because in causal discovery, you have all the nodes, you just want to find the edges. And that's already hard enough. And there's no good way of doing it in scale, right? Because you can only limit it to these are the classes of DAGs that are consistent with your data. And maybe you can keep going from there. But then if you want to have extra action, you're going to need extra nodes. As far as I know, that's completely intractable. Like, how do you systematically add nodes that give you more actions and then connect it to everything else?
Yeah. So there's an open question there, which I don't know the answer to, which is, and there's another problem. So there's one more dimension to the problem, which is the problem of wandering sets, which is some points don't just drift around, they literally just fade away and the new points fade in, right? So we have an action space, it used to work, and now the thing that it worked on is basically just dissolved, right? We don't have that anymore, right? This attractor is essentially vaporized or is in the process of vaporizing. And then there's this new attractor over here, this new thing that's kind of emerging, that's distorting the environment around it. And so we have to be able to discover new actions by him because the underlying system itself is emerging. And so if it's emerging, then everything that can exist within it has to also emerge along with it, maybe?
Yeah, I totally agree. It's an important problem, but I guess the way people have been doing it is just using intuition or whatever, guessing at what are the actions or new sort of, I mean, that's the entire history of, I guess, science trying to guess these structures and actions, right? I guess I just don't know of any current methods that help you do that. I think they're all like super small scale and they work in very special cases.
Right. Right. Interesting.
What about when we have bigger problems where we just ignore that things have changed, right? Our categories are flat out wrong, right? And I think it's easy to prove that, right? Our models are actually wrong.
Right.
And they are not validated by data. It's really easy to falsify, right? I think it's more subtle when people are actually trying to find what's going on. Whereas when we are just like sticking to, no, this is the model, this is the way it works. Like, I feel like there's
that's related. Yeah, that's related to the whole like paradigm shift stuff we talked about, right? The Thomas Kuhn, like there is this sort of conventional way of doing things, and people have been building things on top of it.
Yeah.
And it will take a while for people to admit, okay, maybe the whole structure is wrong and we should do something completely different, right?
Yeah. Sorry, I'm just thinking. It's very interesting.
But I mean, it's really hard to tell if a model is wrong, right? Like it's just a number of accuracy, or it's not always clear. It's 100%. It's never 100% wrong. So probably all models that people take for granted is right many times, like in many situations. Maybe it's just wrong in critical situations, no?
You see, I think there are situations where it's like flat out wrong because of data drift kind of issues, like especially in the medical situation, we thought something for this particular group of people, and then we've changed the group of people that it's being applied to, and it doesn't actually work, and it's easy to show that.
Yeah, but then that's not a problem with the science. It's just problem of practitioners are just crappy. They don't know what they're doing. So that's a different story.
No, it's not actually. It's because we've come to define the problem in a self-referential way. We've lost the fine grain, and we've changed the problem, right? We're no longer trying to fix the fine grain. We have a new definition for it. We've created a new category that new category no longer matches the fine grain of the existing category. Does that make sense?
Yeah, I think it makes sense. So I mean, the solution, I guess, would be to constantly have a process that goes back to the raw data and reevaluates in the light of the new things that we discover. So maybe that link is missing.
Maybe no, I'm certainly not challenging any of it.
Yeah, recognizing that our materializations are no longer working. Maybe we should stop for today and.
Yeah. Sorry, it's very interesting.
Think about things.
Yeah. So I'm hung up on this idea of thingness and being able to essentially make an assessment as to whether something is a thing or not. So that's, I think, what I'll be chewing on over the week, and perhaps we could have a conversation, a narrower conversation next time about that granular piece. Would that be of interest?
Yeah.
Okay, great. Well, thank you, everyone. Very good. Yeah, let's do a call it here, and we'll pick it up next time.
Sounds good.
Have a good week.
All right. Thanks, everyone.
Bye, everyone.
Okay. Take care. Bye.
Bye.